What? Okay, so what I want to do is review kind of, what is the big picture? So in some sense, this course, digital signal processing, is kind of like a discrete time version of signals and systems. And so, we have to understand kind of the key ideas, right? So we have signals, which are basically, the way I think about signals is that they come from, some sort of a sensor or some sort of a program. So they come from sensors, things like thermometers and voltmeters and microphones and cameras and stuff like that. And then systems process signals to produce other signals. Okay. So for example, you have a signal that comes from your gas pedal in your car that goes through some sort of a complicated, system, which we're going to call car, and then the signal that comes out is basically the velocity that drives your wheels, right? And so, this is a probably horribly oversimplified and horribly complicated system under the hood, but that's the idea. Or, maybe I have a CD that encodes a digital signal. I put that into my stereo, which maybe you guys don't even use anymore, and what comes out of my speakers is sound, right? And so it's not like it's a one-to-one mapping between bits of information on a CD and sound that comes out. I think for one thing, this is a digital signal and this is a continuous signal, right? I'm driving a audio speaker that needs a continuous input. And so historically, all this kind of signals and systems stuff was driven by what I would call kind of like power engineering, right? In the early days, if you look at the syllabus for or the plan of study for an electrical engineering student, it was all about motors and circuits and stuff like that. Now a lot of the curriculum is all about passing information back and forth, and the same thing holds true for this. And this kind of formalism is so successful that it's also applied to lots of other fields, like chemical process control and economic modeling and stuff like that. You can often boil all that stuff down into signals and systems. So even if you go off and become a quant on Wall Street, you're still going to be interested in understanding things like Fourier transforms and stuff like that. So, okay. So the key distinction in our class is going to be continuous time versus discrete time, right? And so we already know from signals and systems that continuous time signals basically look like a plot like this, where I have a function of t, I have a signal like x of t, and then that is basically some kind of unbroken line that represents a signal that I can ask at any point in time. Time equals 0.0589, what is the value of the signal, right? On the other hand, in this class, we're really motivated by discrete time signals. And so in that case, we have a function like x of n. And x of n, we're only going to allow that to be sampled at certain fixed discrete intervals, right? So that means that I don't have anything that occurs between the gaps of these stem plots. And so basically, whenever I draw a digital signal, it's usually going to be like this, where I have little stem plots that represent what is happening at every point in time. There is no such thing as x of 1.5 for a digital signal, right? You get only what's there. And so, as you know, there's a lot of theory behind how do I go from a kind of continuous signal to a discrete signal in such a way that I don't lose information. That's what the sampling theorem is all about. We're going to cover that in this class too. And we know that in certain conditions, you can actually sample a continuous time signal so that the samples are good enough to reconstruct the original continuous time signal if you wanted to. So in some sense, you haven't lost any information, right? So we're going to come back to that for sure. Okay, so our focus is on this, especially in this class, because all computers these days are digital. And so that means that even if these are the kinds of inputs that are coming into the system, they still need to be converted to something digital first, and then they are digitally processed to produce some other digital system, and then maybe there's a D to A converter at the other end that converts it back into a continuous time signal if it's needed, okay? But these days, almost all of the processing inside the computer is digital, right? So one thing that we didn't talk about a whole lot in like a continuous time signals class, but that we will talk about in this class a little bit more is not only are the samples taken at these discrete spacings apart, but also in practice, I don't have like infinite resolution on the y-axis either, right? So for example, here, I may only have some discrete locations where my sticks have to fall exactly on one of these things. That's called quantization, right? And so if you're used to listening, if you look in your iTunes drop-down menu about quantization, you can see I've got 8 bits per symbol or 12 bits per symbol, right? That kind of means how finely do I discretize the y-axis? We'll talk about some of the implications of how that works also. Okay. So let's talk a little bit about processing signals, right? So what are the kinds of basic operations that we can do to a signal? So one of the most common ones is flipping. And so, especially if you've done convolution before, you remember there's a lot of flipping involved, right? So if I have some x of n, like this, and I want to look at what is x of minus n, all that means is I'm flipping the samples around the y-axis. So this guy at 0 stays the same, and then I kind of mirror it across the y-axis. Okay. There's scaling. And so if I have, let's use the same x of n, let's talk about what is x of 2n, okay? So the way I think about this intuition is that this is kind of like saying, if I imagine this is an audio signal, it's like saying I'm playing the signal twice as fast, right? That means that the overall duration of the signal should decrease by 2. And so that means what I'm doing here is I'm taking every other sample, right? So what that becomes is something like this. So I'm going to label these samples here. And so, one thing that is definitely true in DSP that was not true in continuous time signal processing is that we lose information, right? So after I do this scaling, I've thrown away those samples in between the ones that I had, and I can never get them back, right? The only conceivable way I can get them back is if that I sample below the Nyquist rate, or above the Nyquist rate, and I can reconstruct the continuous time signal and resample it, right? So we're going to talk about that. If you don't understand that, don't worry about it. So we're going to talk about that later, but in principle, right, for a continuous time signal, I can squish it and stretch it, and I'm not really losing anything, right? But for a digital signal, I'm definitely throwing away stuff, right? And so that's one kind of special case. And so let me just say that samples are lost. Another kind of, let me just say, what would we do with something like this, x of, say, n over 3? That's kind of weird, but it's worth kind of talking about for a second. So what that would mean is that I am kind of slowing down the signal by a factor of 3, which means that it should get broader, right? And so in that case, what that would be for this signal is, well, I got this point, this is what happened at 0. What used to be 1 will now become 3. And then what used to be 2 will now become 6. And so, if I don't do anything else, my expanded signal looks like this. I don't have anything else to put in these middle locations because I don't have any samples to grab from, right? We're going to talk about that after the first exam, but, really, I don't want this. Kind of what I want is something that kind of smoothly interpolates between the samples that I'm missing, right? Again, we can use the sampling theorem to solve that kind of problem. Okay. Any questions so far? And the other thing is shifting, right? So shifting the signal is probably one of the most common things you want to do. So what about shifting? So here, again, I have to remember that in this case, I've always got integers, right? So I mean, if I'm shifting a signal by some amount, it has to be by an integral amount. And so if I have, for example, this is my, I think they're the same thing, right? Integer amount, if you like. Sure. So if this is my, signal here, and I ask about, shifting it by 1 unit, what I get is something like this. And I always did find this, sometimes people find this a little bit counterintuitive, right? This is like saying that if I have x at n minus 1, people think, oh, well, shouldn't that mean that the signal shifts to the left because it's a negative number? The way I think about this is that this number here tells me how am I delaying the signal, right? So this is like saying the signal should start 1 unit later, okay? And you can always confirm this kind of thing by plugging in, right? So if I want to know what is, this is my transform signal, this is my original signal, so I can say, okay, well, that means that y of 2 should be x of 1, right? And I compare that to this, and I see, yes, y of 2 is x of 1. So if you're ever not really sure whether you're shifting the signal the right way, then you can just plug in some numbers to make sure that the things line up the way that they should, okay? So we can combine all this stuff together, right? So how would we handle something that is a little bit more complicated, like this? X of 2n minus 2n plus 3. Okay. So let me draw a little example signal. So let's say this is our example signal. Okay. Well, you have to do these steps in a certain order. Otherwise, you'll get the wrong answer. Okay. And so the order that you should always do it is shift, flip, scale. Okay? And what I mean by that is that I find you never get the wrong answer if you do these operations very mechanically, right? So what I would say is, first I'm going to define a new signal that is x of n plus 3, right? That's just the shifting part. Then I'm going to define another signal that is the previous signal that I got flipped. That's the negative part. Then I'm going to finally get my result by scaling it by 2. And that's the scale part. And again, if I follow through my math, I can see why this works, right? So this is what I ultimately want, right? And so I can say, okay, I'm saying that's w of 2n. I plug 2n into here, and I get z of minus 2n. Then I say, what was z? Z was x of n plus 3. So I plug in minus 2n here, and I get x of minus 2n plus 3. So you can see that it works out, right? And so now I can actually kind of carry out these operations, right? So x of n plus 3, what that means is that I'm kind of delaying things by -3 units, right? That's like saying that the signal should start 3 units earlier. So if these are my time markings on the original signal, my z signal is going to start 3 units earlier, which means what used to be 2 will become -1. I should have left myself more room on the page. Right, so this is my z of n. This goes from -1 to -5. Then I'm going to flip that around to get w of n. That means that this whole thing flips across the axis, and now I'm going to get this, going from 1 to 5. And then I'm going to scale that by 2, which means I'm going to compress it. So what, 0 stays 0. What used to be 2 becomes 1. What used to be 4 becomes 2, and everything else goes away. And so this is my final answer, right? Again, if I wanted to, I could check. I could say, okay, well, what is, y of 2? Y of 2 is x of -1, right? And I can see that, yes, this guy matches this guy over here. What is y of 1? Y of 1 is going to be x of 1, right? So this guy matches this guy. So everything turned out okay. And I am kind of, taking it for granted that anything that I don't plot is 0, okay? So I guess I put a 0 here only because that corresponds to this 0 here. But in general, for a digital signal, if I don't tell you otherwise, all the stuff on the x-axis continues to be 0. Okay, so any questions about this example? Okay. So, some properties of signals that we need to kind of talk about are your old friends, even and odd and periodic and stuff like that. And so, a signal is even if basically it looks the same as itself flipped around the y-axis, right? So a signal that looks like this is even. A signal is odd if it's kind of like the negative of itself flipped across the axis. So by definition, if I plug in 0 here, what I get is this equation, which tells me that the middle entry of an odd signal always has to be 0. And then it's kind of like a mirror image of itself around the y-axis. Okay. And every signal has an even part and an odd part. And so every signal has even and odd parts, which means that I can say, okay, x of n is equal to, well, let me say it this way. The even part of x of n, I can compute it by looking at the signal and flipping it around and averaging those two things. And I can look at the odd part of it by making this computation. So let me just show an example of that in Matlab to make it a little bit clearer. Okay, so let's make some sort of random signal. Make it more interesting. Okay, so again, there's this stem command in Matlab that plots for me the signal. And you can see that this signal is neither even nor odd, right? It's just a bunch of impulses. And to make it easier for me to do in Matlab, what I'm going to do is I'm going to assume that the middle value is 0. I can do that by kind of providing a x-axis here. So now you can see that the middle value here is at 0, and this signal goes between -4 and 4. Okay? So how do I get the even and the odd parts? Well, I'm going to make a negative x, which is basically going to be the flipped version of x. Luckily, there's a Matlab command that lets me do this, flip left to right of x. And so if I make another figure, I can look at that. Right, so here's the original x, move it, and here's the flipped x, right? So I can see that I've mirror imaged these guys. And then if I want to get the even part of x, I would take x plus the flipped part of x, which is neg x, and divide by 2. And the odd part of x would be x minus neg x over 2. And now if I do these things, but did I do this wrong? Oh, image show. I'm teaching image processing instead of DSP. And make this guy here box. Okay, so here's the even part of x, and here's the odd part of x. And I can see that these signals obey the properties that I talked about before, right? The even part is nicely symmetric around 0. The odd part has this odd symmetry. And I can verify that when I add even part of x and odd part of x back together, I get the original signal. So here's the original guy, and here's the original guy, right? So, and I can see why this works. Like if I switch back to my document, I can kind of see that obviously that this plus this, you know, these negative parts are going to cancel out, and these guys add up to just the x of n again, right? What's maybe not immediately clear is why these formulas are guaranteed to produce an even signal and an odd signal. And so that may be one of the homework problems, for example, is proving that this signal has to be even, that signal has to be odd. Okay. So any questions about this example? So the reason we care about even and odd signals will be important when we get to things like understanding the Fourier transform and how the real and imaginary parts of the Fourier transform are related to the signal, stuff like that. So we want to cover that now. Another key property is periodicity. Okay, that was really important in continuous time. It's still important in discrete time. And so periodicity. All this means is that the signal repeats itself after a certain number of integer steps, okay? And so, for example, I could have a signal that looks like this, and I would say that the period of this signal is 4, meaning that it repeats itself every 4 units. And I have to remember that it goes this way, too. Okay. And, you know, actually, a constant signal is also periodic, right? A signal that is the same value all the time. You know, a constant, by its nature, has period 1. Okay? And so periodic signals are going to be super important for us, largely because we're going to be dealing with different kinds of discrete time sines and cosines. Okay. So far, so good. So let's talk about your old friend, the delta function. Okay. So the nice thing is that in the discrete time world, everything is nicely representable by a stick on a graph that you can make in Matlab, right? So no more weird convolution integrals, stuff like that. So special signals. So special signals. So a key one is the delta function, okay? So that's just defined as being equal to 1 at n equals 0 and 0 everywhere else. Very simple. And we represent this with the Greek delta. Okay. Equally important is the step function, unit step function. So that equals 1 when n is greater than or equal to 0, and 0 when n is less than 0. So that means that this is like a signal that is off prior to 0, and then it turns on at 0, and it stays on. And we usually denote this by u of n, where the u usually stands for unit step function. Okay. So as with other electrical engineering classes, it's always really important to label your axes well enough that I know what's on the x-axis, what's on the y-axis, right? So here I'm making sure that you know that the height of these dots is 1. Okay. Now the unit step function and the delta function are related to each other. Okay, and so you may remember that in continuous time there was this kind of derivative and integral relationship between delta and step. Here it's kind of like looking at sums and differences. Okay, and so one thing to think about is that this step function here can be thought of to be made up of a bunch of delta functions, right? That idea of taking a signal apart into its component pieces is really important to what we're going to talk about next. And so one way to think about this is that the unit step function looks like, well, what is the first entry? It's the delta function. What is the next entry? It's the delta function shifted by 1 unit, and then shifted by 2 units, and so on, plus dot, dot, dot. And the way I look about this, the way I think about this more mathematically is this is the sum from k equals 0 to infinity of the delta function shifted by, some positive number of units. Okay. So that's definitely true. That's like taking apart the signal into just its stick pieces. Okay. Another slightly trickier way of thinking about the step function and the delta function is saying, okay, well, let me put this back for a second. Another way I can think about this is just in the same way that when you do continuous time, you have let me just draw the dreaded arrow for 1 second, right? So the way we talked about the step function in continuous time was, question?
Yeah, I was just wondering, would it be from k equals negative infinity instead of 0?
No. Let's look at this again, right? So this is basically saying that the way I get the step function is I take basically this guy, and I add to it this guy, and I add to it this guy, right? But I don't want to add the ones that are negative, right? So it has to start only at 0, right? If I went all the way from minus infinity, I would just have a constant, right? It would just be 1 all the way across. Other questions? Feel free to stop me at any time. Okay, so the way that we talked about the continuous time delta and step was that this continuous time delta function was like a little unit amount of energy that when I integrated across, whenever I bumped across the delta function, I would accumulate 1 unit. And so if I were to look at the integral, I know I promised not to do this, from, say, tau equals minus infinity to t of the delta function, I got the step function. What did that mean? It just meant that if I, integrate up to here, I get 0. If I integrate up to here, I get 0. If I integrate just over the delta function, I get 1, and then I get 1 forevermore, right? So the same way of thinking about it applies to the delta function, right? So here's the delta function. So here's my discrete time delta function. What I can say is, okay, I can think of the unit step function as the sum from k equals minus infinity to n of delta of k. So what does that mean, right? This is a little bit confusing, but let's think about what it means. It means basically, what is the value of the step function at, say, -3? Well, I plug in -3 at this infinite sum, and I ask myself, okay, I'm going to add up all the values of the delta function up from minus infinity up to -3. I add up those values, and I get 0, right? Because nothing has happened yet. So I can put down 0 here. What about unit step function at -1? Again, I add this up, I add up to here, and I get 0. What happens when I put in 0? Well, from -infinity to 0, suddenly I add this 1 unit of stuff, right? So now I jump up to 1. Now suppose I put in n equals 5, right? That's like saying add everything up from the left-hand side all the way up to 5. Well, I've only ever got that 1 unit, right? So basically, after I bump over the 1 piece of stuff in the middle, I never accumulate anything else, right? So this is another way of thinking about the relationship between the unit step function and the delta function that makes it look a little bit more like the continuous time integral version that we used in signals and systems, right? The idea is the same, right? So in continuous time, the step function was what I got by integrating the delta function up to some point. The same thing is true here, except I can't integrate because I'm not in continuous time. The only thing I can do is add, right? So if I keep on adding stuff up, I eventually get things to work out. Okay? So this is kind of like, the analogy between, integration and what I would call a running sum. Okay. So comments or questions on that? Okay. The other way around is a lot easier, right? So we know that in continuous time, if I have my continuous time step function and my continuous time delta function, the idea was that, the delta function is what I get by taking the derivative of the step function, right? So the derivative almost everywhere is 0, right? Whenever this function is flat, I get a 0 derivative, right? The only place I don't get a 0 derivative is where the function jumps up to 1. And that's why this delta function jumps up to 1, right? Technically, the derivative of this function at 0 is not really well defined for what you guys know right now. It's like infinity, right? So it's like the slope is infinitely high. And that's, kind of why we have this arrow here instead of an actual dot, right? That was all very confusing back when you took signals. Life is much nicer here in digital world. So again, here's my digital version of the step function. And here's my digital version of the delta function. And here I can see, how would I kind of do the discrete time version of differentiation? Well, that's like taking a difference between, how did you learn about derivatives in the first place, right? You kind of took a signal and you shifted it a little bit and you subtracted them and you kind of made that shift smaller and smaller, right? So the idea here is that if I look at the shift, the delay of the delta function, step function by 1 unit, if I delay that guy by 1 unit, that means it starts at 1 instead of starting at 0. And now if I say, okay, well, I could subtract this from that, what would be left would be just the delta function. So I could say that the delta function is like the difference between two step functions, right? The shifted one and the regular one, right? And the analogy there is kind of like, this is the analogy that we used in continuous time. The nice thing about the DSP part is that there's no need to understand any of this weird integration, delta function stuff, right? This is very direct, right? I just take this, shift it, and subtract it, and I get that, right? So another way that digital signal processing is a little bit easier than continuous time. Okay. So now I want to kind of put this together, right? So let's talk about, just like I made the step function up out of delta function pieces, I can do that with any signal, right? So let's say, making a signal out of delta functions. So let's suppose I have just some kind of arbitrary signal. Okay. Well, I can write this like just the component pieces. Right? So it's like saying, just give me this stick, and then give me this stick by itself, and then give me this stick by itself. Right? Each of these is like a scaled and shifted delta function, right? And so if this guy was 1 high, and this guy was -1, and this guy was 2, then this is basically like saying, well, this is like 1 times the delta function that hasn't been shifted at all, right? This guy is like -1 times the delta function that has been shifted by 1 unit. This guy is like 2 times the delta function that has been shifted by 2 units, and so on. Right? And so what I can write is that my signal is like the infinite sum from k equals minus infinity to infinity of x of k times delta of n minus k. Right? What that's saying is that at every position, right, so at every value of k, I multiply the delta function by the corresponding value of x. And then I add all those guys up, right? So this is a way of taking apart the signal into each of the pieces, okay? So that's good. We're going to use that formalism a lot when we come to things like, convolution. And sometimes, another way to think about this that's kind of like, there's another way of looking at this. So this is kind of, I forget what I would call this, but okay. So this is one property. I'll draw a box around it. Another property is what's called the sampling property. Which is that, let's suppose I do a similar looking sum. So first of all, let's think about what this means, right? This is like saying, okay, I have a signal. Let's think about that as a signal as a function of k, right? So again, this could be anything. What is delta of k minus n? Well, that's like saying I've got a delta function that is shifted, that is delayed to start at n. Right? So what do I get when I multiply these signals together and add them all up? Well, I'm going to be multiplying together a lot of zeros, right? So everywhere where one of these guys hits a 0, the product of those two things is going to be 0. The only time I'm not going to get a non-zero answer is right at the point where the delta function is firing. And so what do I get at that point? Well, I get whatever this number happens to be. It's like saying I multiply this value by 1. And what I get is x of n. Okay. So again, this is just kind of like an exercise in saying that, I can use a delta function to kind of pick off any value of the signal that I want, right? By multiplying it and adding it up. Okay. Any questions about either of those two formulas? Okay. So, more kind of bookkeeping is complex numbers, right? So everyone has to remember complex numbers from whenever you saw that material, right? So we're going to learn, or we're going to use a lot of complex numbers. So complex number review. So most of the time, or not most of the time, but often we will talk about a complex number like this, where this is the real part and y is the imaginary part. And we call this Cartesian or rectangular coordinates. So sometimes we'll call this like real of z and im of z, where here j is, as we know, the square root of -1, And I think I'm most of the time going to use J in this class and not I. You may catch me using I, but I think that J is better. Another thing you may find is the polar version, which is something like this, where this is the magnitude, which we sometimes call Z in bars, and this is the angle, or the phase, which you sometimes see called like angle of Z with this little angle guy. And this is called polar coordinates. And there are some key relationships between all these guys, right? So the key property that defines these relationships is Euler's formula, which says that if I have e to the j theta, right, that's a complex number that is represented by cosine theta plus j sine theta. Right? So this is the real part of e to the j theta. This is the imaginary part of e to the j theta. That's what I use to go back and forth between converting these things, right? And so if I need to have explicit formulas, that's like saying, okay, if I have a point out here, I can either call it, x plus jy, or I can call it r e to the j theta, right? Those are equivalent ways of talking about the same complex number z out here. And I convert back and forth between them by saying, okay, well, if I want to go from Cartesian to polar, my r is just the hypotenuse of this triangle, and my theta is the arctangent of y over x, right? I'm looking at, this is the opposite, this is the adjacent. And going the other way, if I know the radius and the angle I want to get Cartesian coordinates, then I say that x is the radius times the cosine, and y is the radius times the sine. And all this stuff just falls right out of Euler's formula. You can always rederive this stuff if you need to. Another formula that you probably remember from way back when is that if I want to look at, if I go back to cosine theta, that's the same as this. Your old buddy, right? So why is this true? This is like saying that if I have, cosine theta plus j sine theta plus, if I use Euler on this, I have cosine negative theta plus j sine negative theta. I know that cosine of theta and negative theta is the same, and the signs are opposite, right? So that means that I have 1/2 of 2 cosine theta, which is cosine theta. And the same way, sine theta is 1/2 of, or 1 over 2j of e to the j theta minus e to the minus j theta. So these conversion formula, you're going to need these a bunch to go back and forth between Cartesian and polar and stuff like that. Hopefully familiar. Okay. Any questions about any of this complex number stuff? Okay. So let's talk for a second about sines and cosines, right? So first let me talk about what this is in, that's not how you spell sinusoids. Sinusoids. So let's talk about this in continuous time just for a second, because we're going to use continuous time sines and cosines for sure. Just to know what the parts of these things are, right? So here, this is what I call the amplitude. This is what I call the frequency. And this is what I call the phase, right? And if I were to plot that, basically what I have is a signal that looks like this. So normally, so say the phase was 0, the sine would start right at 0, and it would go like this. If I have a phase shift, that means that things are delayed by a positive or negative amount. And so in this case, what I get is kind of something that looks like this, where the sinusoid goes back and forth between plus and minus a. A is always a positive number. The peak-to-peak period, right, this distance here, we sometimes call this the period, is 2 pi over omega 0. And the phase shift is related to this phi. Just as a quick, check, the sinusoid is not shifted by phi exactly, right? Because this kind of comes back to what we talked about when we do transformations of signals, right? First I do the shift, but then I have to do this scale at the end, right? So this is actually scaled by omega 0 to figure out what the intercept and on the x and y axes are. Okay. So we know from continuous time signal processing that we have this concept of low frequency to high frequency. Okay. So, kind of the lowest frequency, well, the lowest frequency they can get is a constant, I guess. But here's the idea is that, this could be sine t, and then if I have sine 2t, that's something that wiggles twice as fast. Sine 3t is something that wiggles 3 times as fast, and so on, right? And so the idea is there's this kind of continuum from low-frequency sinusoids to high-frequency sinusoids. Okay. Now, we have the same idea here in signal processing, but life is a little bit different and a little bit easier. Okay? I'm going to come to that in just a second. Well, I guess I can talk about it. Yeah, I can talk about it in just a second. Okay. The reason I'm deferring is I also want to mention about exponentials, right? So exponentials are also things we come across in signal processing all the time. So exponentials again, sticking to continuous time for a second, are basically functions that grow or shrink in a certain way. So here, C and A are real numbers. So if A is positive, that means that the exponential is growing like this, right? And the value here is C. And if A is negative, it means that things are shrinking like this. So this is where you get things like, explosions and compound interest and stuff like this. This is where you get things like delay and friction and stuff like that, right? So things are speeding up or they're slowing down. So let's talk for a minute about, how do I handle this quantity when C and A are actually complex numbers, right? That makes things a little more complicated. So what about this signal when C and A are complex? Well, a little tricky, right? So it's not immediately clear how would I handle something like, 2 plus 3j e to the, -1 minus 2j t, right? Does that mean something? Sure it does. And the best way to do it is to convert these numbers from Cartesian into polar coordinates. And so, remember, I can always write C as, let's say, the magnitude e to the j theta, and I can write A as r plus, okay, I guess what I'm doing is I'm writing this in polar and this in rectangular. I guess I'm kind of making things a little bit confusing because I'm using R and C in the wrong way. But all right. So how would I work this out then? I'd say, well, x of t is the polar version of C, e to the Cartesian part of t. And now I can kind of say, okay, I can separate this out into some purely real stuff and some purely imaginary stuff. Purely real stuff is C e the RT, right? That's kind of like saying that I have this real envelope on a sinusoid that looks like omega t plus theta. Or a different way of saying this is that I can now write this like cosine omega 0t plus theta plus j sine omega 0t plus theta. Right? So what I can see here is that the real part, if I forget about the j, the real part is purely a cosine multiplied by this exponential function. And the imaginary part is similar, except it's a sine instead of a cosine. And so what does that kind of mean? Well, if I imagine that this here, suppose that this is a decreasing exponential, what it means is that I have kind of like this envelope. So this is like my envelope of C e to the RT if R is less than 0. And then the real part of the signal is some cosine that is kind of, oscillating within this envelope. Like that. Right? If R equals 0, then I don't have any oscillation at all, just a regular cosine or a sine. But if R is negative or positive, then I either have an expanding cosine or a contracting cosine. So what it comes down to is that this thing is kind of this complex, it's not purely a complex sinusoid, it's modulated by this exponential function. But it has a notion of a frequency, right? I can't really say that this function is periodic because it doesn't strictly repeat itself, right? It's always changing its amplitude. But there is this sense of a period inside this envelope, okay? And so that's why sinusoids and exponentials are kind of related to each other. That's why I want to talk about them together. And so life is similar in discrete time, right? This is all continuous time stuff, but in a similar way, we're going to come across signals that are kind of like this, where I have a discrete time signal that is some constant times some number to the n power, which I can think of as constant, e to the bn, where alpha is e to the b, right? And this is exactly in the form of this, this time domain exponential time sinusoid. So again, I could say in the same way, this is like this. Some real part and some imaginary part. Okay, so last thing I want to talk about is kind of periodicity in the discrete time world. Okay, so we talked about how in the continuous time world, I could have sines and cosines that just keep on increasing in frequency, right? So if I look at this picture, there's nothing to prevent me from continuing to oscillate faster and faster, right? So I can talk about cosine of 40,000, I can talk about cosine of 40,000 hertz or 400,000 hertz, and things can just go faster and faster. But that is not true in discrete time, okay? So discrete time sinusoids are a little bit different. And a key reason for that is the following. So let's take a look at, suppose I've got some sort of a sinusoid of, so here's an example of a discrete time sinusoid. What is e to the j omega 0 plus 2 pi n? Okay, so this is like saying, okay, I'm going to take my frequency and I'm just going to add 2 pi to it, right? So that, in theory, in the continuous time world would be a faster, a higher frequency sinusoid. What happens here? Well, I can work this out. I get e to the j omega 0 n plus j 2 pi n, which is like e to the j 2 pi n e to the j omega 0 n. But now I see that, n is always an integer, right? We're in discrete time world now. So what that means is that, if I think about n equals 0, that's like saying e to the j 0. That puts me here on the circle. If n equals 1, that means I come around and I've gone one full circle, so I get e to the j 2 pi. That's also 1. If n equals 2, I've gone around twice and I have e to the j 4 pi. That's also 1, right? So this whole guy turns into 1. And that means that when I add 2 pi to any frequency, I end up getting the same frequency again, right? This means that there is no kind of like infinitely high frequencies in discrete time world. We can only go up to a certain amount. In fact, that, we now have this idea that there's only a 2 pi wide kind of range of frequencies in discrete time. And that's good, right? So just in the same way, if I have omega equals 0, what does that mean? That's like saying e to the 0n. That's just constant all the time, right? So just like in just like in continuous time world, the lowest frequency thing I can get is something that's just constant, right? So here, this is like lowest frequency. What's the highest frequency thing that I can get? Well, the highest frequency thing I can get is something that basically is flipping back and forth as fast as I can possibly make it go. And that's simply this signal, right? So this is about as fast as I can make a digital sinusoid go, right? It alternates between its maximum and its minimum amplitude as quickly as possible, right? And this is corresponding to omega equals pi, right? Because e to the pi n, well, if n is even, I get an even multiple of pi, which means I get 1. If n is odd, I get an odd multiple of pi, which means n is minus 1, right? That's like saying that the signal is bouncing back and forth between here and here on the complex plane, right? And so this is high frequency. And so what this means is that in DSP, we no longer have to draw these kind of charts of frequency that kind of go arbitrarily far out on the x-axis, right? We're going to draw a lot of pictures in this class that fundamentally look like this. So for example, if I want to design a low-pass filter, so let's say a discrete time or digital low-pass filter, what that would look like would be something like this, where I say, okay, this is high frequency, and for reasons that we'll talk about in the next couple weeks, there's a symmetry that basically will say for most of the filters that we care about, the frequency response will be symmetric around 0. That means that I could have a filter that looks like, this is like the ideal low-pass filter. And in practice, we're going to talk about how I can't obtain this low-pass filter with a limited length or finite impulse response filter. So in practice, the filter that we design may look something that's more funky like this. And you may have remembered seeing some pictures like this back in continuous time signals. So we're going to talk about, how do I make my actual design filter frequency response look as close as possible to this. That's a topic for a different day. So last thing I want to mention, so let me pause and ask. Any questions about that? Okay. Last thing I want to say is that, you need to be careful when assessing whether a given signal is periodic in the discrete world, right? So you're probably used to thinking that, well, any cosine is periodic because that's what cosines do, right? That's not exactly true. So when is e to the j omega 0 n periodic? And remember, this is discrete time. Well, what that means is that I have to have e to the j omega 0 n plus n, capital N, equal this for some integer n. Right? So here, not immediately obvious, so that means that this has to be e to the j omega 0 n, e to the j omega 0 capital N. I need this guy to equal 1, right? And what does that mean? That means that I need to land over here on the complex plane, which means that this number, this omega 0 n, has to be, basically some even multiple of pi, right? This has to be either 0, or it has to be 2 pi or 4 pi or something for some integer. Okay. So that means that my frequency has to look like this. Or kind of conversely, the period looks like this. So let me just make this a little bit more concrete, right? So let's suppose I have cosine of 4 pi over 5. Yeah, that's my signal. Well, let's go back to my formula here, right? This is like saying this is my formula for the period. N equals 2 pi k over 4 pi over 5. I need this to be an integer, right? So what do I get? I got basically, bless you, I basically 10 pi k over 4 pi, which is the same thing as saying I have 5 over 2k. So for this to be an integer, I need to have k equals 2, which means that n equals 5. So this signal is periodic with period 5. And I can verify that if I just go over here. So if I have, some time domain thing, and I say that x is cosine of 4 pi over 5 times n, and I plot these guys. Right, so I can see here, I can see here that this is indeed, touch screen, this is indeed periodic with period 5, right? It repeats every 5 units, starting at 0, and then I get this kind of weird behavior, and then I get this repeat over here at 5, right? But not every discrete time thing that looks like a cosine is periodic, right? What about, x of n equals cosine of 7n, right? So normally in continuous time you'd say, yes, this guy is periodic and it has a period of 2 pi over 7. But 2 pi over 7 is not an integer, right? And furthermore, there is no integer that will, basically make this guy some integer value, right? Nothing I can do. So what does that mean? If I were to look at cosine of 7n over here in Matlab, whoops. So if I were to look at cosine of 7n, I can see that things are kind of periodic, but not exactly, right? So you might look at this and say, oh, okay, well, these guys look pretty much like a period of 7, but actually here, you can see that this stem, if I were to zoom in on this, which is hard to do, actually maybe it's easier just to look at the numbers. Right? So there is no like exact repeat here. These guys here, sure they happen to coincide, but then I've got this number and this number don't match, right? These are numbers that are kind of not ever going to sync up into a period, right? So that means that we care about very particular, cosines that are periodic in discrete time world, right? We're going to talk about a lot about that when we talk about the Fourier transform and the Fourier series for digital signals. Okay, so that's where I wanted to get to today. Any comments or questions? All right, so in that case, hold on.